Hello, ENIGMA-U students, and welcome back to our statistics lecture series. Today, we're going to be digging a little deeper into some of the descriptive statistics that we talked about in the last lecture, specifically central tendency and variability. We're going to split this lecture up into two parts. The first part, we're going to focus on central tendency, then we'll take a break, and then we'll come back and talk about variability in the next video. Okay, so at the beginning of all of our lectures from here on out, we're going to have a tools you will need section where I lay out some of the symbols, some of the formulas, and then some of the concepts that we're going to be discussing in this lecture. If there's a lot of them that we will have talked about before, such as scales of measurement, which we talked about in the last lecture, but then there will also be some new concepts like frequency histograms and polygons, and then procedural rules for using our summation sign. Okay, so descriptive statistics are exactly what they sound like. They are statistics that describe the distribution of scores, that describe a data set. The ones we're going to be focusing on specifically are central tendency, variability, and shape. Let's begin with central tendency. So, excuse me. Central tendency, the goal of this statistic is to find a single value that is most representative of the center of a distribution. So there are three different types of measures of central tendency that we use because there's not going to be a single standard procedure for finding the middle or center of a distribution. There's no one size fits all. It really depends on the data set. And so we're going to learn throughout this lecture which of these three is best in which situations. So the first we're going to talk about is the mean or the average. Then we're going to discuss the median or the middle. And lastly, we'll talk about the mode or the most frequent data point. So let's begin with talking about the mean. So the mean is going to be the numerical average or the balancing point of our data set. If you think about it in terms of if you laid your whole distribution on a plank, just like this, and your data points are represented by blocks, your mean would be where you would have to put the fulcrum right here so that the plank was perfectly balanced. It's the balancing point. Other ways to think about it are the weight of all the values on one side are going to be balanced with the weight of all the values on the other side of the mean, or mathematically, the total distance to all of the scores above the mean is equal to the total distance of all the scores below the mean. This is how we calculate it. This is the formula for mean. We take the sum of all of the scores in the distribution and we divide it by the total number of scores. Here are some properties of the mean. So the mean is what we call sensitive to the exact value of all the scores in the distribution. What this means is when you change the value of one score in your data set, that will change the score of the mean. It's especially sensitive to extreme values called outliers. So if you have an extreme data point, really a lot lower or a lot higher than the majority of your distribution, then your mean is going to change more. What we just talked about here, introducing a new score or removing a score changes the mean unless the new score equals the mean. But an interesting facet of this is if you add or subtract a constant to every score in the distribution, the mean is going to change by that constant. So here's an example. If we take this distribution, these original grades, and we add 2 to every single one of them to get this distribution now, these curved grades, we can see that our mean, which was originally 89, we're going to do the same thing, just add 2, and our new mean is 91. The same thing works if you multiply or divide by a constant. So here we have a distribution. We multiply every single one of our points by 12 to go from feet to inches if you do not use the metric system. And our mean was 13 with the original data set. But now we're just going to multiply that mean by the same constant, 12, to get our new mean, 156. That's pretty cool. Another interesting point is that the sum of all the deviations from the mean will always equal 0. So if you take a data point and find the distance from the mean and add them all together, it's going to equal 0. Under most circumstances also, the mean is the least subject to sampling variation, which just sampling variation is basically if a statistic is going to be different based on the sample that you draw. The mean is going to be pretty consistent in any sample in a population compared to the other measures of central tendency. So the next one we're going to talk about is the median. The median, instead of being the balancing point, is now just the midpoint. It's the middle. Half the values are above it and half the values are below it. It's the score that divides the distribution exactly in half, the 50th percentile. A key point here is we're not just locating the midpoint between the highest and the lowest values. You're not just saying, okay, I'm going to take the highest value minus the lowest value, and I'm going to find the one in the middle. Sometimes it works out that way, but what you're actually doing is you're organizing your values from smallest to largest, and then you're finding the one that's exactly in the middle. So if there's an odd number of values, you're going to select the score that's exactly in the middle. Here we can see there's 1, 2, 3, 4, 5, 6, 7 scores above it, and 1, 2, 3, 4, 5, 6, 7 scores below it as well. If there's an even number of values, you're not going to have an exact middle score. So you're just going to take the average of the two. These are the two middle, and then the average of 4 and 5 is 4.5. So that would be our median. So some of the properties of a mean is that, of the median, excuse me, unlike the mean, it's unaffected by extreme scores or outliers. The median is less concerned with the numerical value of the data points and more with just how many data points there are, if that makes sense. If you add, it doesn't matter if you add a 10 or a 1000 to the end, the median's only going to shift over 1. However, it is more subject to sampling variability than the mean. So what that means is your median isn't going to be as consistent among different samples from the same population as the mean is. If a distribution is symmetric, like this one down here, the mean and the median are going to be the same thing because the mean is the balance point. So in a symmetrical distribution, it's exactly in the middle. And then the median is the middle point. So it's always going to be in the middle. If your distribution is not symmetric, your mean and median will not be in the same place. And we'll get more into that later. This is an interesting point as well. The mean is defined by scores with equal distances above and below it. The median is defined by scores with equal frequencies, an equal number of scores above and below it. And finally, we're going to talk about the mode, which is just going to describe the most typical or commonly occurring score in a frequency distribution. Basically, which data point appears the most frequently. Here, we can see that 8 appears 3 times, which is more than any of the other data points, so 8 is our mode. The disadvantages of the mode, or a key point is, the mode is the only measure of central tendency that needs to correspond to an actual score in the data. The mean and median can correspond to an actual score, but they don't need to. The mode always has to be an actual score that is represented in the distribution. The disadvantages of the mode are that it honestly ignores a huge part of the data, which is why we don't really use it when we're summarizing quantitative data. We use it in very specific situations, which we'll talk about later. And another note is it's possible to have no mode if all of your values are the same, or more than one mode, either a bimodal or multimodal distribution. So now let's go through some of the various shapes of distributions and compare where we would find each of the measures of central tendency in relation to one another. If you want, you can pause the video before I explain why the central tendency measures are where they are and see if you can reason through that yourself. So for this first section, we're looking at a symmetrical unimodal distribution. Unimodal just means there's one mode. In a symmetrical unimodal distribution, your mean, your median, and your mode are going to be the exact same place. Your mode is pretty easy to find on a graph. It's just the highest point, the x value that has the largest frequency. The median is the middle, so it's going to be in the middle. Cut that symmetrical distribution in half, and then your mean is also going to be in the middle because each score on the left corresponds with the score on the right. This is also a symmetrical distribution, which means the mean and the median are going to be in the same place, remember? But since all of our x values have the exact same frequency, they appear the exact same number of times, there's no mode in this distribution. So mean and median are the same, but there's no mode. This is a symmetrical distribution again. So Remember, in a symmetrical distribution, mean and median are always in the same place, but this one is bimodal. So that means it has two modes. The two high points, one is right here and one is right here. Two modes. This is also a bimodal distribution, but it's our first asymmetrical distribution that we've looked at. So it is bimodal, and I know what you're thinking. This mode looks a lot higher than this mode, and that's true. This mode appears much more frequently than this one does. So why are we calling it bimodal? Why don't we just determine that this one's the mode and leave this one apart? The purpose of a mode is to determine the relative, the purpose of a mode is to determine which x value or which data point is higher relative to the rest of the distribution. And obviously this one it's the highest, but in the context of the shape of this graph, this is also a high point. So anytime there's a peak in your distribution, that's going to be called a mode. So there's two modes here. The median is going to be exactly in the middle of your x-axis every time, but then your mode, or your mean, is going to be pulled towards towards either your outliers or where the majority of your data sets are. So since there's a lot of x values over here with a high quantity of them, the mean is going to be pulled over in that direction. Conversely, now we're looking at skewed data sets. So in skewed distributions, there's a strong tendency for the mean, the median, and the mode to be located in different but predictable places. So let's look here first at a positively skewed. Positively skewed just means that the skew or the tail is on the positive side of the x-axis. So here, your median's exactly in the middle, your mode is at the high point of the graph, but your mean is always going to be pulled, remember, towards your outliers. These are our outliers here. So the mean is going to be pulled more towards the outliers than the median is. Same thing is true, but just flipped for a negatively skewed graph. Mode is at the high point, median's in the middle, mean pulled towards the outliers or the tail. This is how we're going to choose the best measure of central tendency. I'll let you go through this graph yourself, but I'm going to point out a few key points in how to choose which measure of central tendency best represents your data set. Generally, the mean is going to be a very good measure of central tendency because it uses every score in the distribution and it's closely related to your measures of variability. So it's going to be a pretty good measure to use generally, but there are a couple instances in which you cannot use the mean. Number one is if you have any extreme scores or outliers. In that case, your mean is going to be skewed. So you're better off using your median because it's a little more stable and robust. If you have any undetermined values, so if you have occasionally a situation where an individual is going to have an unknown or an undetermined score, for example, like if you're measuring the number of errors or if someone did not complete their task and you don't have a value for them, you can't use the mean because it's impossible to compute a mean with an undetermined value, right? So in that case, you would also have to use the median. And the last case when you can't use the mean is in an open-ended distribution, when you don't have an upper or a lower limit, because that's also going to be impossible to compute the mean with. In that case, it's also better to just use the median. A situation in which you would use the mode is if you had nominal or ordinal data, especially if you have nominal data, it's not numerical, so you really can't use the mean, and you probably shouldn't use the median. In that case, the mode's going to be the best. If you have ordinal data, you could use the median or the mode. Remember, ordinal data is when we have it on a ranking scale. And in that case, the median or the mode would be appropriate. Okay, before we finish here, let's do a little bit of practice. I'm going to read, we're going to read this together, and then I'm going to have you pause the video, try to figure this out yourself, and then we're going to come back and I'll tell you the answers. So this is a situation in which we have the salaries of 7 teachers in a school district who've been involved in contract negotiations with the district, but the negotiations have reached an impasse. Both parties have decided to take their case to the people through the newspaper ads. The district wants to show that the teachers are already well paid, whereas the teachers want to show that they are underpaid. So what we're going to do is we're going to find all the measures of central tendency, the mean, the median, and the mode, and then you're going to tell me which measure of central tendency each group would be most likely to use, and then which measure of central tendency would actually be the best choice. So take a second, pause the video, figure this out on your own, and then I'll come back with the answers. Okay, so now we're back. Let's calculate these together. So, oops. So the mean, remember what you do for a mean? I just gave you a little spoiler, but the mean you should have gotten is $26,571. We take that by adding up all of the salaries and then dividing it by the total number of subjects. So we have 1, 2, 3, 4, 5, 6, 7. So we take the total of the salaries, divide it by 7, and you should get this answer. Your median should have been 22,000. If you take all 7 and rank them from smallest to largest, and then pick your middle value, that's 22,000. And then your mode, you can just see by looking, it's going to be 19,000. That one appears 3 times, which is more than any of the other salary points. So which group or which measure of central tendency would each group be most likely to report? The school district, I think, would be most likely to report the mean. Oh, this is just showing it to you on a graph, or the mean, because it's the highest. So they want to show that their teachers are already well paid. Whereas the teachers themselves would probably report the median or the mode, because it's, I would say, probably the mode to show that they are underpaid. Again, another example of how these are all measures of central tendency, but they all tell different stories, right? And then finally, which measure of central tendency would be the best choice as the representative center? The median would be the best choice in this situation, because we have an outlier, which means that our mean is going to be skewed, and probably shouldn't use that, higher than it really should be. And then the mode is just a little bit lower and doesn't really tell us about the center of our distribution here. So with that, we're going to take a break and then come back and talk about variability in our next lecture.